Okay. So far we have seen linear programming, which means linear objective, linear constraints, and linear variables. So variables were continuous. So when we defined x1, x2, so we have put greater than equal to 0, right? Or in non-standard forms, it could be unrestricted or less than equal to 0. Fine. So now you look back and see that when you were talking about this Toyco problem, the number of toy cars, toy trucks, and toy trains, or the ready mix model, that is the number of tons of exterior paint and interior paint to be produced, right? Or the sweet shop example, where the number of son papdi, number of batches of son papdi and rasgulla to produce, right? So if you look back at these problems, you will understand, the values of these decision variables are often desired in discrete quantities, not in continuous quantities. Which means that, say for example, toy cars, this Toyco problem, right? Now at the end, the manager would want a result as an optimal solution, right? Some discrete quantity of these toy cars. So you would like to say that, these 100 units of toy cars, 100 units of toy cars or 250 units of toy trains, to be produced, right? Now, incidentally, what happened for the kind of problem that we have considered, for the kind of data, it turned out so, like these discrete quantities. But if you look at the problem structure, the variables, they are allowed to take even fractional values, because you have defined x1, x2, x3 greater than equal to 0. So it can be 100.5 as well. That is also a feasible solution. Now for the kind of data that we have used, we were lucky that we got these discrete values, right? But it is not so for general problems of LP. So for general problems of LP, you can get fractional values, right? So so in that case, you would see that, your program may suggest that 100.5 number of toy cars to be produced, which doesn't make much sense in real world, right? In some cases it may make sense. Say for example, a ready mix model, if you say 100.5 tons of exterior paint to be produced, so this is implementable in practice, but certainly not 100.5 number of cars, toy cars, right? So for some products, continuous variable is acceptable, because they are practically implementable, while for some other products it is not so, right? So there is an additional restriction on the variables which require it to be discrete, right? Now this is also known as discrete programming, discrete optimization, or integer programming. Okay, some of you might have already heard of this term, discrete optimization. So discrete optimization is nothing but, solving for a problem, optimization problem in discrete space, which means that the values of the variables are restricted to take only discrete values. Hmm. In operations research, we call it integer program. The resulting program that we get is called integer program. So let us see what is the use of this integer program, and why simple round off from the LP optimal solution would not work. Because many of you might be thinking that, okay, if I get an LP solution, say 100.5, I can easily round it off to the closest integer by applying some, ceiling function, or floor function, or whatever it is, to round it off to the nearest integer value. But why? I mean, these may work or may not work, and we will see an example, and you will realize that this is not guaranteed to work, and in most of the cases it won't work. Um, Now for this chapter, you can refer to this book, Hamdi Taha, Operations Research and Introduction, and also Hillier and Lieberman, which was earlier shared with you, Introduction to Operations Research, right? And this is an advanced book Nemesher and Woolsey, integer and combinatorial optimization, right? Now this is not available. This may be available online, but only some restricted chapters. I'll try to send you those chapters. So this is an advanced book. So if some of you are interested in research in integer programming, right, or discrete optimization, then you can refer to this book to know more details and more advanced topics. But for this course, the first two books should be sufficient. Okay. Now, so first is integer. So we are now defining some terms. So first one is integer linear programming. So what is integer linear programming? We know, or you already know linear programming. That is when the linear objective and linear constants. When you have additional integer variables in the system. Okay, so variables are restricted to take only integer values. We call it ILP. But your objective and constant should be linear equations form, right? So then it is called ILP. Then we have this term mixed integer program. Mixed integer program means we have a mix of variables. So some variables are allowed to be continuous while some others must take discrete values or integer values. So we have a mix of variables. Okay. Then we have binary integer program. Binary integer program means the variables of the program, they are restricted to take only 0 or 1. So that is binary. Only 0 or 1. Even not any other integer like 2, 3, 4, it cannot take. Only 0 or 1. So that type of program is known as binary integer program. So we'll see their examples now, like, So some practical examples, let us consider and see that how we can formulate some real life problems as an integer program, and then we'll see how to solve it. So let us now focus on the modeling part, which means if some problem is given, real life problem, then how to model it as an integer program, and then we'll come to how to solve it. Okay, what is the algorithm to solve it? Because clearly here, simplex won't work, and I'll tell you the reason later that why simplex won't work here. So right now, let us focus on the formulation part. Now, this capital budgeting problem. This is a very common problem which is faced in uh, companies, in many companies and industries, right? Where suppose they have conceived 5 projects and their estimated costs or expenditures in terms of $1 million per year. So each project spans through 3 years, and the cost for each year is given. Okay, and then the expected returns. So if you successfully complete this project 1, you are expected to get a return of $20 million. So expected returns are also given in $1 million in the right hand side column, right? And then in order to run these projects, you have to incur some costs, right? Some infrastructure costs, labor costs, procurement costs, many costs are there. So you need to invest. Now you have available funds per year for these projects. So total available funds for first year is 25, second year is also the same, second and third year same one. Now the company wants to decide that which projects are the most profitable to run under these conditions. So you know the cost expenditures, you know the returns, you know the available funds per year. So clearly, ideally, a company would like to run all the 5 projects, right? But why it is not able to do so? Because of the availability of funds. See 25. So if it runs all projects, it will exceed this available fund limit. Now you have to choose that which projects to run and which not, in order to maximize your return, maximize your total return, right? So how do you formulate it? Can you tell me how do you formulate it, this problem? So what are the variables, decision variables, objective and constraints that come to your mind?
So there will be 5 binary variables corresponding to each project.
Right. So here the company wants to decide whether the project one will be executed or not. Correct. So clearly this is a case of binary variable. So we define x1, x2, x3, x4, x5 as binary, 0 or 1. So G1 means being executed, 0 means it is not. And you want to decide which value it takes in the optimal solution, right? Okay, great. And what about objective function?
The returns 20x1, 40x2, 20x3, and so on.
Huh?
The returns, the total returns from the project, 20x1 plus 40x2, and so on.
Right, total return from the project. So 20x1 plus 40x2, like this, sum of all this return. Good. And what about the constraints? So a funding constant is there, available
Expenditure,
funds.
yes.
So the
So you
availability
have
of funds per year.
Hello, sir.
hello, am I audible?
Yeah, now you're audible. Before this, you were
Okay.
not audible.
Yes,
Okay,
sir,
okay.
you're audible.
There is some problem happening at my end. Is the slide visible?
Yes, sir.
Okay.
Yes, sir.
Yeah, yeah. So now you see, so this was the formulation, right? Now, if you suppose you have a method, I will not discuss about that method now, the solution method, but suppose some black box is there to which you pass this problem and then you get this optimal integer solution, okay, which tells you that this first 4 projects should be opened and that 5th project should not be run, and you get $95 million as your total expected return, okay. Now, suppose if we tried to solve this problem using the LP method, the simplex method. So what we would have done, we would have, say, relaxed these 5 variables as continuous variables. So let them take any value between 0 to 1. So you'd have defined x1 is between 0 to 1, any value, any continuous value, right? Similarly for the other 4. So then it would have become an LP, linear program, and we know how to solve the linear program by using simplex, and we would have got this solution. So this is called relaxed LP solution because we have relaxed the integer constraint, right? So this solution we would have got if we would have solved by LP. So apparently it seems that the profit, it was earlier 95, now it is 108. So it has increased. Okay, but we have to see that whether you see that value of x1 is 0.57 and x5 is 0.73, so which doesn't make sense practically, like in terms of decision making. So then some of you might be thinking that let us simply round it off to the nearest integer value, and then we have the optimal solution. I mean, we can compare it with the optimal integer solution. So if you do that, what is the solution you will getting? Suppose you do a simple round off to the nearest integer. What will be the solution from this LP?
All, if you do nearest integer, then all variables will become 1. Like
All
it's
all variables will become 1. But if all variables become 1, that
it
it
won't
is
All
affect
constraints will
function.
be violated.
not possible. It is not a feasible solution, right? For the original problem, integer problem. So you see the simple round. So this is a very simple example. So like this, many other examples you can see where this rounding off doesn't work at all. So you need to have a separate method to solve an integer program, which we'll discuss, which is called branch and bound. So it's a divide and conquer strategy, which we'll discuss later on. So this gives you the motivation why you need to study the integer program separately. It is not like linear program. Okay. Now, let us try our hands with another modeling example, which is set covering problem. Those who are from computer science background might have already heard about this problem or might be familiar with this problem, set covering. So this is, say this is our a small campus of some institution, say IIT Kharagpur. This is a small portion of the campus. Okay, so these are some streets, and then you have these junctions, which are these intersections, 1, 2, 3, these nodes, right? The problem here is that you just 1 minute. The problem here is, say you need to install a Wi-Fi infrastructure, Wi-Fi device at these nodes, at the intersections. Now the condition is that if you install install the Wi-Fi device in one node, the intersecting streets, that means the incident edges which are coming to this node, will be covered by that device. So you will get the Wi-Fi connectivity only on the incident edges, right? And the institute wants to minimize its cost. That means it wants to identify minimum number of such nodes and their locations, so that this entire graph, that means all the edges, are covered by the Wi-Fi network. So how to model it as an integer program? Okay, so manually, can you tell me, manually you try different combinations, can you tell me that what is the optimal solution? Minimum number of nodes, and which are those nodes which can cover this entire network? The condition is that if you install, say for example, if you install the device at 1, it will cover street A and street G. If you do it at 2, it will cover street A, street F, street I, street B. So all the edges that are incident on it will be covered. One edge can be covered by two. That is not a problem. But all edges must be covered by at least one Wi-Fi device. So how to solve this? Try it. So now you are seeing, slowly you are moving from engineering, core engineering background to management. So all these decisions that you are taking, in operations research, so they are relevant to managers of the company. So this operations research is also known as management science. And if you, some of you might go for MBA in IIMs, right? So there you will be having one vertical called operations management. So OR, operations research, is the basic tool for OM. So many decisions related to OM, operations management, are taken from OR by using OR. Of course, another being statistics and machine learning. So these tools are there. So three tools: optimization, statistics, and machine learning. So these three are three basic tools for management nowadays. So how you represent this problem? What are the variables, first of all? So manually, could you figure out that what should be the locations?
Yes, sir. Like as someone already wrote in comments, but I'll repeat it. Like 8, 2, 7, and 5.
8, 2, 7, and 5. Right.
And that
Great.
is optimal because like you can there are 4 edges which don't have common endpoints actually.
Mhm.
So from each edge, one node should be contributing compulsory. So minimum is 4, and we found a solution with 4 nodes, so that is optimal.
Okay. So there could be other solutions as well, multiple optimal solution, right? Say for example here, say 1257. What about 1257? Does it cover 1257?
Yes, sir.
Hmm. So it's an example of, see, multiple optimal solutions, which you have also learned in LP, right? That it is possible to have multiple optimal solutions. So this is an example of that, right? Okay, great. Now for this small graph, you could actually manually figure out, by trying out different combinations and seeing. But suppose you have 100 edges, this type of network with 100 edges or 1000 edges, will you be able to find out manually? No, right? It is not possible. For complex networks and of large size, you need then again a program to decide, right? What is that program? Then how do you write that program? Optimization program. So how do you write the decision variables and the objective and the constraints?
For each node, we keep one binary variable.
So because the decision here is that whether to install a device at a node I or not, correct? So for each node, I have a decision variable, binary, x1 up to x8, correct?
Yes, sir.
Now, okay, great. Decision variables are done. Now, what about the objective? What do you want to achieve in the objective? You
The
want to
minimum
minimize
number.
such number.
Minimize some of those binary variables.
Yes, so minimize some of those. So minimize x1 plus x2 plus x3 up to x8, right? Great. Now coming to the constraints. What would be the constraints?
Like if we take like if there are two nodes, say 1 and 8, like they have an edge between them, so we have to keep x1 plus x8 is equal to 1, like since that edge has to be covered.
Correct. So here the condition is covering constraint, that each edge has to be covered, right? So for each edge you will have a covering constraint. And how to write that covering constraint? That it should be covered by at least
Yeah, yeah, so
one
it should be greater than or
edge.
equal to 1.
Yes, should be greater than equal to 1. So at least covered by 1 in one of the endpoints, right? So for street A it will be x1 plus x2 should be greater than equal to 1. So either x1 or x2 should be 1 to cover street A. So very simple. Now, so we have written this, minimize this sum subject to, for each street we have this covering constraint. Understood? And then when you will solve it again by a method, the branch and bound method, which we'll discuss later, you will get the solution 1, 2, 5 and 7, or maybe the other one, right? If you have multiple optimal solutions. Okay. Now these are some techniques which you should know for formulation or modeling purpose. Suppose so far we have seen simultaneous constraints, right? So when you write an LP or an integer program, you have seen simultaneous constraints. I mean, all the constraints are satisfied together simultaneously. But in some cases, it may be either or. So if I write either this or this x1 plus 4x2 less than x, so this becomes either or constraint. Now how to handle? Because in simplex method we have what we have seen. In simplex we have simultaneous systems of equations, and then which you transfer it to a table or in a matrix form and then solve it. It's very easy if you have simultaneous. But if you have either or, then this is not simultaneous system of equations, right? You cannot convert it to a simultaneous system. So then how to handle it? So you have to make it simultaneous, and this is a trick to make it simultaneous. So what I have done, you see, in the right hand side I have added big M y. Y is an auxiliary variable which is 0 or 1, binary variable. So I have added another decision variable y, which is binary, and a big number, big M. And in the second, I have added plus big M 1 minus y. So what is actually happening here? So it is actually, now these two are simultaneous, but it has either or a structure. This either or a structure is maintained. You know why? How it is maintained? Can you explain? Suppose y equal to 1. Suppose y takes value 1. Then what will happen? If y is 1, then the right hand side will become 18 plus big M, which means big M, because 18 is very small number compared to big M. So what will be happen to this first constraint? It says 3x1 plus 2x2 less than equal to a very big number. It is as good as saying nothing, because anything that is everything is less than a very big number, right? So which means this first constraint becomes inactive, right? I mean, it is non-existent now. And the other, what happens to the other one? When y equal to 1, it becomes 0, right? So it becomes x1 plus 4x2 less than equal to 16, which is this constraint, right? Which means that this is now enforceable. So you see, when y equal to 1, the second constraint is enforceable, while the first constraint vanishes. right? Similarly, when y equal to 0, the first constant is enforceable and second constant vanishes. Is it happening or not? So it has that inherent either or constraint. So either this constraint is there or that constraint is there. So this is a trick to convert the either or constraint into simultaneous form. Understood or not?
Yes, sir.
Yes. So similarly, how to represent either or variables? What is the either or variable?
Y into x1 plus 1 minus y into x2.
Right. So if we say, yeah, so in that case, either this variable will be one or the other variable, right?
Yes, sir.
Yeah. So can you do a quick assignment on this, that y equal to say minimum u1, u2, where u1, u2 are some numbers, real numbers, say 2 and 3. U1 is 2 and u2 is 3. So what is the value of y? It will be 2. Minimum of 2, 3 is 2, right? Now I want to write this formulation as an LP or as an IP, to find y. Then how to do that? So I want to put this entire thing in a format of optimization program, which is some objective should be there, some constant should be there, decision variable should be there. So how to write a formulation of such kind?
Sir,
Yeah.
the objective function is minimizing y into u1 plus 1 minus y into u2, and y is the binary variable.
No. See, y is
I mean, okay. So I didn't mean this way, but okay, let me change the variable name. Okay. Objective function is x into u1 plus 1 minus x into u2, where x is a binary variable. X,
then
x, x into u1 plus 1 minus x into u2,
okay.
and x will be a binary. So I think that should be fine.
No, but then what is the
Minimizing that
constant?
objective. Minimize objective function is x into u1 plus 1 minus x into u2, and we want to minimize that.
Okay. And
And
then what is the constraint?
like
U2 minus U1 greater than 0 or something it will be.
but u1 and u2 are already defined, right? Or is it variable again?
No. U1, U2 are given. Say
Yeah,
2 and 3. They're
yeah.
given.
Then only one. There will be only one constant, like x. X should be binary variable. Like x should
X
be
is
0 or
binary,
1.
right? So X is binary, that is fine then. So it can take, X can take 0 or 1, anything.
Yeah.
Okay. Then which value it will take?
Depending on whether u1 is minimum or u2 is minimum. So if u1 is minimum, it will take 1.
Mm-hmm.
If u2 is minimum, it will take 0.
Right. Everybody got it or not? Everybody got it or not?
Yes, sir.
Okay,
Understood.
good. Now, let us now look at some other problems which are well known, well known problems in integer programming, and they are also applied in some, in many operational domains, right, in business. So one such is knapsack problem. So what is a knapsack? What is the English meaning of knapsack?
Like some bag, something like that.
Mm-hmm.
Some bag which can hold something.
Right. So suppose you consider cargo plane, aircraft. So an aircraft has certain volume, to carry the load, right? Suppose this capacity is given. Small b is the capacity of that aircraft. Say in terms of tons, say 100 tons or 50 tons. Actually, it is not so high. Normally, practically, it is within 10 tons. So let us, for example, let us take 10 tons. Okay. So 10 tons is the maximum capacity, load capacity of the aircraft. And you have many types of loads available of many, volumes, right, which are to be loaded onto the aircraft, but you cannot accommodate all at one go. So you have to decide which loads to be transported, I mean, at that point of time, so as to maximize your some objective. It may be in terms of profit, it may be in terms of delivery time, right, or any other objective, right. So this type of problem is very common in manufacturing and service sectors, where you have certain capacity and you have to profitably decide, intelligently decide that which items to be loaded or to be produced, to maximize uh, the maximize your return, right. So this problem is known as knapsack problem. So it is similar to having a bag and you have many items. Suppose a thief, it has entered a house with a bag and so many items are there in the house. Now it has to choose that which items it will put into the bag. How it will decide? How the thief will decide that which items to be put in the bag? Of course, he will target first the precious items, right? Expensive items, isn't it? Why he is targeting expensive items to be first put in the bag? Because you want to maximize the return, isn't it? So here for each product, which has different volume, which is say AJ. You see here given is AJ. AJ is the volume of the product, and then CJ is the return, the profit associated with that product or value of the product, right? And the knapsack problem tells you they maximize this total value of the product to be put in the bag. So summation CJ XJ such that the volume of such products, all the products that are put in the bag, so that is the summation of AJ XJ is less than equal to small b. Small b is the capacity of the bag. X is binary. So X belongs to binary space, right? So whether to put an item in the bag or not, that is the decision. So it's binary. This is the maximization objective, and this is the constraint, which is called a knapsack constraint or capacity constraint. Okay, so this is an example of simple knapsack problem. Now there could be multi-dimensional knapsack problem. Multi-dimensional means there are many bags of different capacities. So earlier we were considering one aircraft which has capacity of 10 tons. Now there could be multiple types of aircrafts. Say 3 types are there, different models, right? So they have different capacities. One is 10 tons, another one is 8, another one is 5, right? Then you have to decide that which item will go to which aircraft. to be loaded to each aircraft. So this is an example of multi-dimensional knapsack problem. Why knapsack problem is knapsack constant is so important? Because we are, see, this is nothing but the standard constraint which we were encountering since the start, like less than equal to type. So right hand side was the capacity, availability, right, and left hand side is the consumption or the the operational total operational times and things like that. So this less than equal to type which we know as a standard constraint is nothing but the knapsack constraint. Okay, so this is another problem. Another problem is assignment problem. So what is assignment problem? Let us take again another real example, which is say say again from the aviation sector, if you look at, say there are some aircrafts available, so 10 aircrafts are there and 10 crew members are there, crew teams are there. Now each crew will charge differently because their experience level is different, pilot and all, suppose a variable pay system. So depending on their experience, each crew team, each crew will charge differently, right, for the aircraft that it flies, and that is given by CIJ. So CIJ means if crew I is flying aircraft J, then this salary you have to give CIJ. Okay, so now you have to decide that which crew to be allotted or assigned to which aircraft. So this is an assignment problem, that because you are assigning crew to aircraft. So what is the objective function here? Of course you want to minimize the cost in terms of salary and all, right? So here it is minimize summation double summation Cij Xi. Xij, how it is defined? Xij is 0, 1. So that means if crew I is assigned to aircraft J, then it is 1, otherwise it is 0. Fine. So sum of this is the total salary that you give for the assignment. Then what are the constraints? What are the constraints? Now suppose if the problem is symmetric, that means that 10 crew are there and 10 aircrafts are there. So then each crew will get one aircraft. So then these constraints for each crew, you have summation Xij is 1. That means for each crew they are assigned to exactly one aircraft. And the second constant will also be equal to 1. For each aircraft they will get one crew, exactly one crew. But suppose it is asymmetric. Suppose the number of aircrafts is higher than the number of crews. So some aircrafts will lie idle, will not be assigned. So in that case, summation Xij will be less than equal to 1. Right, so it can be 0 also for some of the aircrafts. So it's a general form of assignment problem which is asymmetric. So in symmetric case, all the constraints will be equal to. In asymmetric case, some constraints may be less than equal to. Are you getting it or not? Any question?
No, sir.
Okay. Now, I pose you this question. Can you solve this problem without using any solver? So usually see either one approach could be you relax these Xij variables as continuous, taking any value between 0 and 1 and solve it by simplex. Then you may get fractional values, but for this problem it won't happen, and there is a reason behind this. So I'll not go to those mathematical details. So if you look at this matrix, it has some special structure, this constraint matrix, which is called totally unimodular. So for totally unimodular matrices, even the linear program will always yield integer solutions. So even if you solve it as an LP by relaxing these xij variables, you will get the xij values as either 0 or 1. And this happens because of the totally unimodular property of the matrix. So you read about it, those who are interested, that what is totally unimodular and why does, if some of you are mathematically inclined, you can read about it and understand. Okay. The next question is that this type, especially this problem, this assigned problem, can be actually solved by a simple algorithm. You do not need any simplex or any other, branch and bound method, any complex thing to solve it. This can be actually done. This can be actually solved by a very simple algorithm called Hungarian algorithm. So I want you to read on your own what is this Hungarian algorithm, okay, and how it is used to solve an integer an assignment problem.
So that's
Okay.
so this Hungarian algorithm is the same one for minimum matching, like minimum matching, right?
Yes, yes. Matching problem. Assignment is basically is a matching problem, right? That you are matching the crew and a aircraft, correct? So you read about this, what is this Hungarian algorithm and how it is applied to solve the assignment problems. Okay. So now, in the next class, I'll talk about this traveling salesman problem. So as you can see, this assignment problem, knapsack problems, these are all real world. So these are basic problems, but you can see so many applications in real world. But of course, they will be more complex and many more constraints will be there in those systems, right? So similarly, TSP is another problem, traveling salesman problem. So it is you, some of you might have already heard of Hamiltonian cycle, right? Hamiltonian. So it is basically that Hamiltonian, how to optimally form that Hamiltonian cycle for a given graph. And this type of this problem is applied from this the online food delivery, the Swiggy and all, right? Then app cabs, and then even in space, say satellite refueling. Suppose 100 satellites are there in the space and one satellite goes from the earth to refuel all these 100 satellites. So in which order they will visit the satellites? What should be its path and route? So that can be decided by solving a corresponding TSP. So it has many applications. So we'll discuss about it in the next class. Okay, so we are stopping here.
Hello. Hello.
Yes, yes. Tell me.
Sir, actually, we have a gate exam tomorrow, sir. Like, can you please extend the time of the tomorrow's assignment?
No, actually, this assignment that I gave today.
I mean, the one which is due tomorrow, sir.
No, that is so you were supposed to do it by today. Today you were supposed to see actually show it